So for our lab 3, we decided to display the clock and the output of our ALU using the 7-segment display, and we decided to use the LEDs on the board as a temperature gradient, where they light up as it gets hotter. So in order to do this, we started with a module called Top, where we instantiated all of our um, following modules from there. So then from there, we use the finite state machine module, or FSM, in order to determine which anode will be lit up using the clock from our faster clock divider. So from here, we're going to move on to our SB deck. This is important because this is how we save the 16-bit input for each number. Because on our FPGA boards, we only have 16 switches. So we decided to use an AB mode, which determines whether it's the least significant, most significant bits of either A or B. And then we toggle a latch switch, which allows it to save. And so we decided that when AB mode is 0, it's the most significant bits of A. When AB mode is 1, it's the least significant bits of A. Then for AB mode is 2, it's the most significant bits of B. And when it's 3, it's the least significant bits of B.
Next up, we have our module TempTop, which takes in the clock, reset, and outputs an SCL and LED num, which corresponds to the number of LEDs lit up on the FPGA board, the Arctic 7. The in-out here, corresponding to SDA, communicates with the temperature sensor via I2C communication. Within this module, we instantiate three different other modules: I2C master, I2C master, and ClockGen were taken from FPGA Dude online from GitHub, and TempDeck was our own module which we added to decode the outputs of I2C master. Within TempDeck, we pass the temperature data which we get from I2C master and decode it into a bunch of 16-bit numbers which correspond to the number of LEDs lit up on the board.
And so each LED, these 16-bit numbers, each of them corresponds to every 1 is when an LED is lit up, a 0 is when it's turned off. And so as a result, as the temperature increases, the LEDs light up from left to right. This recording is where we're testing our temperature sensor. So we put our thumb on, it raises, and then we take our thumb off, and it goes back. So in this clip, what we're doing is we're just reprogramming the device and allowing the clock to run, just to show that the clock can run from 0 and it can carry over into the next bit of hex.
Shown here is a demo of the A-1 mode of our ALU. The lab assistant will switch the rightmost bit corresponding to the least significant bit of the 8 major bits of A. Next up, the lab assistant will switch AB mode to 1, signifying that the switches now correspond to the least significant bits of A. Now the lab assistant switches the least significant bits of A from 0 to 7, showing how the A-1 function works.
So at this part, we're just testing our 16-bit adder to make sure it properly adds. We're flipping the mode to mode 5, which is the adding one. And now I'm flipping through each A, B, most significant, least significant, to make sure it properly adds and gets the proper result of 1414 in hex. So for our lab, we decided to use the 7-segment display. We wanted to maximize what it had, so we used all 8 digits, 4 to output a running clock, and the other 4 to output the output of the ALU.
Because we used all 8 digits, we still wanted to use the temperature sensor and output a temperature reading of the environment, but we didn't have any room on the 7-segment display, and so we opted to output the reading onto the LED line, and having the number of LEDs that lit up correspond to a predetermined temperature setting.
And so the other thing we really wanted to do was take our 4-bit adder from Lab 2 and turn it into a 16-bit adder. And the biggest challenge with this was figuring out how we were going to use the switches. But we decided we were able to use sequential logic by using a toggle switch, like a latch switch, that will latch the values for the most significant and least significant bits of A and B and save them so we can add.
Well, the design seemed to be successful in every aspect that we attempted. The most difficult part would have been the implementation of the 16-bit adder and the idea of the latch switch. Having that in code terms was rather difficult to come up with, but it's a simple concept once it's implemented.